Okay, so are you ready to dive into like the biggest mystery in physics?
You know, it's a big one when it's got a name like quantum gravity.
Right, it's like the ultimate physics puzzle. Even Einstein supposedly couldn't crack it.
Yeah, he spent years on this, supposedly.
Like, how do you even begin to make sense of both general relativity and quantum mechanics at the same time?
Those two are like the titans of modern science, and we're trying to make them do a tango.
It's like they work perfectly fine on their own, but when you try to combine them, everything just
The
explodes.
equations literally just break down. It's
Yeah.
wild.
I know. It's like the universe is telling us, nope, you're missing something big here.
Yeah, and that's something, that missing piece is quantum gravity.
Okay, so imagine this. Okay, we have these two sets of rules governing the entire universe.
On one hand, you've got Einstein's general relativity explains how gravity works on a massive scale.
Right. Planets orbiting stars, like bending around black holes, all that cool stuff.
It's like the very fabric of space and time warping and stretching under the weight of existence.
And it's not just theoretical mumbo jumbo either, right? This
Yeah.
is stuff we see and measure.
Exactly. It's what keeps our GPS systems working.
Yeah.
It's the reason why apples fall down instead of up.
Okay, so Einstein's got the big stuff covered, but then things get really weird.
Oh yeah, because when you zoom in, way, way in past atoms, even down to the tiniest particles,
We enter the quantum realm.
cue the spooky music.
It's like a whole different set of rules. Suddenly everything's blurry and uncertain.
Nothing is absolute. Everything's up for grabs. It's all a cosmic game of chance.
Particles can be in multiple states at once. Things pop in and out of existence.
It's enough to make your head spin.
Seriously. But here's the thing. Both of these theories are incredibly successful in their own right.
They're both backed up by tons of experiments and observations,
But then you try to apply them both at the same time, like inside a black hole.
or at the very beginning of the universe, and bam, everything goes haywire.
So what's the deal? Is it just that the math is too complicated?
It's deeper than that. It's
Yeah.
like we're trying to understand a painting using only the language of music.
We're missing the bigger picture.
Exactly. We need a new language, a new framework that can bridge this gap.
Enter quantum gravity, the holy grail of physics.
The theory that could potentially explain everything in the universe, from the smallest particle to the largest galaxy.
No pressure or anything.
Right. And you know what's even wilder? Physicists have come up with some seriously mind-bending ideas to try to figure it all out.
We're talking extra dimensions, loops of gravity, even the possibility that we're all living in a hologram.
It's enough to make you question everything you thought you knew about reality.
Okay, let's start with the one that's been around the longest and probably sounds the most familiar, string theory.
Yes, string theory. The idea that the universe is made up of these tiny, vibrating strings of energy.
Strings. Okay, like how tiny are we talking? Smaller than an atom?
Smaller, way smaller. Think of it like this. Every note you hear on a guitar comes from a different vibration of the strings.
Okay.
So in string theory, these tiny vibrating strings are like the fundamental notes of the universe. And different vibrations create different particles and forces.
So all the particles we know and love, electrons, quarks, all that stuff, they're just different vibrations of these strings.
That's the idea. And here's the kicker. Gravity is built right into this model.
Okay, I'm listening. Tell me more about how gravity fits into this whole string symphony.
Well, imagine this, one of those tiny vibrating strings could be the graviton.
The graviton.
Yeah, the theoretical particle responsible for gravity,
Yeah.
the one that physicists have been chasing for decades.
So you're saying gravity isn't some mysterious force, it's just another note in this cosmic concert.
That's the beauty of string theory.
Yeah.
It unifies all the forces of nature into one elegant framework.
I have to admit it's a pretty compelling idea. But there's a catch, isn't there?
You've heard about the extra dimensions, haven't you?
I have. It's hard to ignore that part of string theory, extra dimensions. Really.
Yeah. To make the math of string theory work, you need more than just the three spatial dimensions we experience every day.
Wait, so you're saying there are more dimensions than just up, down, left, right, forward, back?
That's right. String theory suggests that there could be 6 more spatial dimensions curled up so small that we can't even see them.
Okay, now my brain officially hurts. 6 extra dimensions, what would those even look like?
That's the million-dollar question. We don't know for sure. Some physicists believe these extra dimensions could be home to other universes, a whole multiverse with its own set of physical laws.
Okay, well, hold on. So our universe is just one tiny bubble in a much larger multiverse.
That's one possibility. But even if we never directly observe these extra dimensions or other universes, string theory has already had a huge impact on theoretical physics.
Like what?
Well, for one, it's inspired new mathematical tools that are being used in other areas of science. And it's given us a framework for thinking about the universe in a completely new way.
Okay, so string theory is definitely out there, but it's also pretty cool and kind of terrifying at the same time.
I'd say that's a pretty accurate description of most things in quantum physics.
All right, so we've talked about strings now. Let's move on to something that sounds like it belongs in a Salvador Dali painting, Loops of Gravity.
Ah, yes, loop quantum gravity.
Ugh.
This theory takes a completely different approach to the quantum gravity problem.
Instead of smooth, continuous space-time, it proposes that space-time itself is woven from tiny, indivisible chunks.
Like pixels on a computer screen.
So space and time aren't smooth and continuous, they're more like a digital mosaic.
Exactly.
Mm-hmm.
And in loop quantum gravity, these tiny chunks of spacetime are constantly interacting and exchanging information.
It's like the universe is doing some kind of cosmic knitting project.
That's one way to put it.
Yeah.
And because of this loopiness of spacetime, there's no such thing as a singularity.
Wait, what happens to black holes in the Big Bang if there are no singularity?
They still exist, but in a different form. In loop quantum gravity, as you approach an extremely dense region like a black hole, spacetime itself becomes so granular, so pixelated, that the idea of a singularity, a point of infinite density, just doesn't make sense anymore.
So loop quantum gravity rewrites the rules of the game instead of trying to work around them.
Exactly. And it offers some really interesting solutions to some of the biggest problems in cosmology.
Okay, I'm intrigued. Tell me more about this loop quantum gravity thing.
For example, some loop quantum gravity models suggest that our universe could have actually bounced into existence from a previous universe.
A cosmic rebound. So there was something before the Big Bang.
That's the idea. It's called the Big Bounce.
Okay, my head is officially spinning now. But as wild as this all sounds, does loop quantum gravity actually have any evidence to back it up?
That's the million-dollar question, isn't it? It's really hard to test these theories because the effects we're talking about are happening on such a tiny scale.
Like trying to find a needle in a haystack, but the haystack is the entire universe.
Pretty much.
Yeah,
We need to figure out ways to look for those tiny quantum loops.
I guess that's why they call it theoretical physics.
Exactly. But even though we haven't found direct experimental proof, yet loop quantum gravity still has a lot of physicists excited.
Because it's just so darn elegant.
That's part of it. It just seems to fit together so neatly. And it offers solutions to some really big problems that other theories struggle with.
Like the whole singularity business.
Exactly. Loop quantum gravity could be the key to finally understanding what happens at the heart of a black hole or the very beginning of time.
Okay, so we've got strings, we've got loops, and now we're venturing into territory that's even weirder.
You ready for the holographic principle?
Hit me with it.
All right, so imagine this. Our entire three-dimensional universe, everything we see and touch and experience,
All the good stuff.
all of it. It might just be a projection of information stored on a distant two-dimensional surface.
Wait, what? You're saying that reality as we know it is basically a giant hologram.
That's the basic idea?
Okay, I think I need to sit down for this one. So you're saying that everything around us is just an illusion? Like a movie being projected onto a screen?
Kind of. Like a hologram. The information about our three-dimensional universe could be encoded on a two-dimensional surface.
But where would this surface even be, like at the edge of the universe?
That's one possibility. We don't know for sure.
This is blowing my mind, but how did anyone even come up with this idea in the first place?
It actually came from studying black holes.
Black holes always seem to be at the center of the weirdest stuff.
They do, don't they? So here's the thing. Black holes have this strange property. Their entropy, which is a measure of how much information they contain, is proportional to their surface area, not their volume.
Okay.
So weird, right? You'd think that something as massive as a black hole would contain an infinite amount of information.
I mean, it does suck up everything around it, right?
Right. But this entropy thing suggests that all the information that falls into a black hole isn't lost. It's actually encoded on its event horizon.
The event horizon being the point of no return around a black hole.
Exactly. So anything that crosses that boundary, its information gets smeared onto the surface.
Okay, so it's like the universe's ultimate recycling bin.
In a way. And if this is true for black holes, some physicists believe it could be true for the entire universe as well.
So you're saying that our entire universe is like one giant black hole?
Not exactly.
Yeah.
But the universe does have its own event horizon. The boundary beyond which we can't see because light from those regions hasn't had time to reach us yet.
Because the universe is expanding.
Exactly. And some physicists believe that all the information about everything that happens within our observable universe could be encoded on this cosmic event horizon.
Okay, I think I need a minute to process this whole hologram thing. It's like someone just told me the Earth is flat again.
It takes some getting used to.
Hmm,
But the holographic principle isn't just some crazy idea. It has some pretty deep implications for our understanding of reality.
like what?
Well, for one, it could help us solve one of the biggest mysteries in physics, the black hole information paradox.
Right, the whole information can't be destroyed, but black holes seem to destroy everything.
Exactly. But the holographic principle suggests that information isn't really destroyed when it falls into a black hole. It's just transformed into a different form, encoded on the event horizon.
So black holes are like cosmic hard drives storing information on their surface.
That's a good way to put it. And this has profound implications for our understanding of reality itself.
Okay, how so?
Well, if the holographic principle is true, it means that our everyday experience of living in a three-dimensional world is just one way of interpreting a much deeper and stranger reality.
So you're saying there's a whole other level of reality out there beyond our perception.
That's one possibility. And understanding this deeper reality could be the key to finally unifying general relativity and quantum mechanics.
Okay, so the holographic principle is mind-blowing and potentially groundbreaking, but where does it stand in terms of actual evidence?
Well, it's still very theoretical, but there are some intriguing hints from areas like string theory and black hole thermodynamics that suggest it could be on the right track.
So like the other quantum gravity theories, it's a wait-and-see situation.
For now, yes. But the holographic principle has definitely captured the imaginations of physicists, and for good reason.
It makes you question everything you thought you knew about the universe.
Exactly. And who knows, maybe someday we'll have the technology to test these theories and finally unravel the mysteries of quantum gravity.
Until then, we'll just have to keep exploring the stranger side of physics.
That's what we're here for.
I gotta say, all this talk about holograms and hidden realities has me feeling like I'm living in the Matrix.
I know it's a lot to wrap your head around, but that's the thing about quantum gravity. It forces us to rethink everything we thought we knew about the universe.
So where do we even go from here? We've got string theory with its extra dimensions, loop quantum gravity with its pixelated space-time, and now the holographic principle with its mind-bending idea of reality as a projection.
It's like we've stumbled into a cosmic choose-your-own-adventure novel, and we're not sure which path to take.
Right. They all sound kind of crazy, but also kind of plausible in their own weird ways.
That's the beauty of it all. We're exploring the very edge of human knowledge, and there's no guarantee which theory, if any, will turn out to be the right one.
So how do we even begin to test these theories? They all involve things that are happening on such a small scale or such a large scale that they're practically impossible to observe.
It's definitely a challenge. But physicists are coming up with some pretty ingenious ways to look for clues.
Like what? Give me some hope here.
Well, on the experimental side, we've got particle accelerators like the Large Hadron Collider, smashing atoms together at incredible speeds.
Trying to recreate the conditions of the Big Bang in a test tube.
Exactly. And by studying the particles that are created in these collisions, we might be able to find evidence for things like extra dimensions or the fundamental loops of space-time.
So it's like we're trying to smash our way to a deeper understanding of reality.
In a nutshell.
Yeah.
And then on the theoretical side, we have mathematicians and physicists working on developing new mathematical frameworks that can help us describe these complex ideas in a more rigorous way.
So it's a two-pronged approach, experiments and mathematics working together to unlock the secrets of quantum gravity.
Precisely. It's like we're building a bridge from both sides, hoping to meet in the middle.
And who knows what we might find when we get there. It's like we're explorers charting unknown territory.
Exactly. The search for quantum gravity is an adventure. And like all great adventures, it's not just about the destination, it's about the journey.
It's about pushing the boundaries of human knowledge and expanding our understanding of the universe and our place in it.
And who knows? The discoveries we make along the way could revolutionize our world in ways we can't even imagine.
New technologies, new forms of energy, even new ways of understanding the human mind.
The possibilities are endless. And that's what makes this such an exciting time to be studying physics.
So to wrap things up, we've taken a deep dive into the weird and wonderful world of quantum gravity, explored some of the leading theories, and pondered the mind-blowing implications of this research.
We've learned that the universe is a much stranger and more mysterious place than we ever imagined.
And that the journey to unravel its secrets is just beginning.
So keep asking questions, keep exploring, and most importantly, never stop being curious about the universe and all its wonders.
And on that note, we'll wrap up this deep dive into quantum gravity. We hope you enjoyed the ride.